you don't do, well I'ma make hella sure that I don't become you. I have no regrets, yeah, I'll tie up my chest. I'll never forget what it's like to be in debt. Been stabbed in the back bed, I'll show you what happens. Pass me the mic and I'll show you with action. I feel this pain, you already know. Turn that to gains, let my money show. I've got these things that I can't let go. Watch me turn this life into something that you could never own. I feel this pain, you already know. Turn that to gains, let my money show. I've got these things that I can't let go. Watch me turn this life into something that you can never own. So fight and die for the things you know you love. Do what you think is right and see life do what you want. So fight and die for the things you know you love. Do what you think is right and see life do what you want. So give me all the scars, I'm a human being. Cover them with tattoos so you can't see. Knew it from the start, you had problems with me and the things I could be, I just wish I had seen. I feel this pain, you already know. Turn that to gains, let my money show. I've got these things that I can't let go. Watch me turn this life into something that you can never own. I feel this pain, you already know. Turn that to gains, let my money show. I've got these things that I can't let go. Watch me turn this life into something that you can never own. So fight and die for the things you know you love. Do what you think is right and see life do what you want. So fight and die for the things you know you love. Do what you think is right and see life do what you want.
Losing time, I'm fading fast. I just wanna make it last. Try to let go of the past. I close my eyes, embrace the blast. Sleepless nights and headaches stack. Restlessness to hell and back. What's my purpose? What do I grab? A slippery surface, a heart attack. And sometimes you just gotta believe there's something that'll give you relief. There's something that'll have what you need, what you need. We're broken, it's tragic, we're not all elastic, but maybe there's magic. Believe you could have it, and I know of sadness, the anxious and panic, the infinite vastness of all that is blackness.
searching for greatness in a sea of the dying and shameless. A sea of the aimless. I don't wanna be one of the nameless. I'ma wake up with the mindset that one day I'm gonna make it. And I don't think I'll be fine if I don't break my limitations. Don't try to stop me, I exist to write my own story. I'll make a decision if I want some peace or if I want the glory, yeah.
Good morning, everyone. Happy Wednesday. I hope everyone enjoyed their Monday off and celebration in honor of MLK. How's everybody doing today in the chat? So just a few reminders. We have lab today. So it'll be lab 2. And so let's just look at, so the materials for lab are now in Blackboard. So they are, of course, under content. Let me turn off this edit mode so you don't see all my junk. Chem Labs, Lab 2, and so there's some data files that go along with it. I kind of changed the labs to Part D. Is not part of this video, but I'll add Part D hopefully today, and along with the Excel files for it. And then you have the documents. And then, of course, I look forward to seeing a few of you in person. Just let me know if you'll be there, not be there, and whatnot. Any other questions about the lab? So let's look at chapter 12 today. So we're starting alkanes. And we kind of talked about alkanes when we looked over our functional groups. But let's just look at them a little bit deeper now. So we have we'll start off with our acyclic alkanes. So this just means a chain of alkanes. And so this can be, the simplest one is methane, so CH4. And that has that tetrahedral geometry, if you remember. sp3 hybridized carbon there. Oops, I did not want to make that go. And then ethane. And so remember, I posted here the prefixes that indicate how many carbons. So methane is 1, ethane is 2, and again they end in that ane. So ethane. And continuing on propane. And so if we look at this, so we can look at our formula. So let's draw out the formula or write out. So this would be CH4, ethane is C2H1, 2, 3, 4, 5, 6. Propane is C3H1, 2, 3, 4, 5, 6, 7, 8. So I dropped that hydrogen. And so all these straight chain alkanes, or all these chain alkanes, so no ring, that's called no degrees of saturation, unsaturation. So unsaturation is either caused by rings or double bonds or triple bonds, of course. But in this case, we have none of that with any of these, again, called acyclic alkanes. So they do not have this, and so that means that they have this formula CN H2N plus 2, where N is the number of carbons. And so just looking at propane, if we plug in 3, so 3 for N, so 2 times 3 plus 2, so that gives us 8 there. So that matches with the pattern we were seeing. And so we often use this term saturated hydrocarbons to describe this, where they have hydrogens everywhere. And so now this is just an example of a straight alkane in nature, undecane. So this is a moth pheromone. Pheromone. I can't spell, so if you're in the chat, just can correct my spelling. So now let's look at kind of the 3D structure again in these molecules. I have different kits. So just to show you a different style, because I'm going to use a different style when we get to different and larger molecules. So this is, I call it my baby model kill kit set. It is specifically for organic chemistry. And so you can see that most of these carbons these are all sp3 hybridized, so you can tell they have 4 places to make a bond. And if nothing on there, you generally, assume, or they provide little white hydrogens to put on, but it can be pretty time consuming. So let's start with methane. And so if you have kits at home, now would be the time to pull them out. So there's that other molecule kit, and then I'm going to put actually the white hydrogens just take me a minute. All these hydrogens have sticks in them. There we go. Ah! So those are both methane. And again, we're observing its tetrahedral shape, symmetric around that rotation axis. So very symmetric molecule. So I'm just redrawing this in 3D. So tetrahedral is our shape at the carbon. sp3 hybridized. So now let's look at ethane. And so ethane, I'm just adding another carbon. And so now I'm just adding in my hydrogens. So there's ethane. So we can have rotation around this bond, which we'll look into. But notice the structure. So right, linear. So it's still in a chain, basically. And so we can draw that. And actually, its preferred geometry is more like that, but we'll look into that just in a little bit. So drawing my 3D structured. So the way I'm drawing it, it's called staggered. So notice I don't have the hydrogens kind of in line, so they're drawn like that, as opposed to what's called eclipsed, where they're in line. So this is staggered. And we'll learn that this is the preferred conformation. And then so let's add propane and see what that 3D structure looks like. And I actually have propane in my mini molecule kit there. So you can see 1, 2, 3 carbons, and imagine each of these points here is a hydrogen. So I don't have the white balls on there explicitly. And then I'm also doing it in my larger structure, so you could see the 3D shape. And so this is why it's kind of important to, if nothing else, kind of look at these on the internet and get an idea of their 3D shape. But I do encourage the use of molecule kits. And again, the school does have them to check out, so we can always arrange that if you'd like to borrow some. And so here's both. Get methane out of here. So here's my both representations of propane. And so now you notice it kind of goes up. So it's not just in a chain, right? So it's not like a straight chain. Kind of makes, I draw it in like a zigzag if I'm just drawing shorthand. And so that's why. So again, we notice it's tetrahedral at each center. So you can just keep going and making either a straight chain alkane, where it's kind of that zigzag up and down, or start branching off. And so let's look at butane and isobutane. And so this is just what we were discussing. So we could either keep making a long chain, or we could branch off. So what are the two possibilities here for, I guess, how to draw 4 carbons? So we're at propane. And then we want to add one more carbon. And you also have to think, well, what's going to give like a symmetrical structure? And so what I mean by that is we could add carbon to each side, or either side. And this is where it's easier to see with this kit. And so there's butane, so it probably wouldn't be like that. Make our little zigzag. You can see. Get some contrast on there. So that's one possibility. So it doesn't matter. So that's our straight chain. So 1, 2, 3, 4. That gives us one structure. Now where else could we put it? Again, I'll go back to propane. So if I put it on this end, results in the same thing, that straight chain butane. But I could put it on this middle carbon. So I'll draw it out as well. Oh my gosh. There we go. And again, each one of these terminal points should have a hydrogen on them. So you can just imagine that. And then, so this is isobutane. So we have 1, 2, 3, 4 carbons. Fill in all the hydrogens. And again, tetrahedral at all of those points. Even this one, so you can tell where that hydrogen would be pointing. So still tetrahedral. And then the formula will still be consistent. So we have 1, 2, 3, 4 carbons. So C4, then H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that matches with our formula of CN H2N plus 2. So plug in 4. So 4 times 2 is 8 plus 2 gives us 10. So any questions on that so far? All right. So let's look at how to classify these carbon atoms as well. And so the name of kind of how we call these carbons also depends on the number of carbons directly attached to, in this case, the red carbon. Let's go back to our class name. And so methane is unique. So methane is a unique situation. It's not attached to any carbons. And then we can have what's called a primary carbon. So a primary carbon has one carbon directly attached. So we're looking at this carbon over here on the right. We notice it's attached to one. And so this is a methyl, our primary carbon. So looking over at this next one, so this is called a secondary carbon. So notice it has two carbons attached to it, two hydrogens. And so just showing this back, right, that's similar to this carbon on propane. So this carbon would be a methylene carbon or secondary carbon. Then you can have a tertiary carbon. And so that would have been like we saw in the butane case. So if we look back at our isobutane, so looking at this carbon on isobutane, it's attached to three carbons. This one would be that one hydrogen poking out. So that would be a tertiary carbon. And then we did not draw one. But look at this. So this is 1, 2, 3, 4, 5. So this is probably isopentane. And so that would be a quaternary carbon where it has 4 carbons attached to it. So let's look at bond rotation. So let's go back to our ethane. And so we had mentioned that with this single bond, we can have free rotation. So let's draw that out. And so this is kind of the distinction between double and single bonds. So single bonds do have rotation, double. Now you have two, so you're not going to have rotation, since that would break your second bond, your pi bond. But the sigma bond is just here, so there can be rotation around it. And if we look at the rotational energy barrier, though, we find that there's actually some preference. And so what you actually find, so even though there is free rotation, but there's a slight difference in the energetics of the two structures. And so we have what's called our staggered versus our eclipse conformation. And so this is for ethane. And so it's showing it as it cycles around. And so what happens is in this eclipse conformation, so again, they're kind of directly behind one another, and it's usually drawn, so you could draw it kind of in this top-down view like this. So this is your carbon, hydrogen, hydrogen, hydrogen. Your second carbon is hiding, and then you just kind of draw your other hydrogens poking out. And so this would be the eclipse conformation. So this is slightly higher in energy. You can imagine, because we have some sort of interaction here, so that's not favorable So they're trying to take up space. And so it's more favorable to be in that staggered conformation, where they're more like that. And so we notice the staggered, and it's relatively small, so it's only a difference of 3 kcals per mole of energy. But you will find that if you could just take like a snapshot of ethane, it would mainly be in the staggered conformation, I believe like 95%. So there is staggered. All right, so let's practice some naming. And so our IUPAC rules for naming, and this is why we'll go through it all together. So we want to kind of identify the longest chain, identify and name any groups attached to it, then name the chain consecutively, starting at the end nearest a substituent group, designate the location of each substituent group by appropriate number, and then assemble name, listing groups in alphabetical order. And of course, we use these prefixes to designate several groups, but are not considered when alphabetizing. All right, so to practice this, let's write out all the possible names of alkanes that have the molecular formula of C7H16. And there are 9 of them. And so I'll give everyone a minute or so to get a head start. And just start by drawing out your structures, and then which ones, are kind of identical, which ones are different, and we'll go over them. So before we do this, I wanted to interrupt you because I said this. I misnamed something. So when we were looking at this structure, and this will be good practice. So what was the name of it? I mistakenly said isopentane, but that's not correct. It's more, I'll say informal name. And this is what I was thinking of, but didn't say, was neopentane. But what else could we call it? So it said, and let's just go through this. So find and identify the longest continuous chain. Well, we have, and this is where you kind of have to look. So you have this 1, 2, 3 chain, or this 1, 2, 3. So you can make a lot of 3 chains. But in this case, it doesn't matter because the things that are attached to it are also carbons. So priority would matter if we had like chlorines on there, but in this case all the same. So we could just assign this one as our chain. So we have a propane chain. We have 2 methyl groups on there. So this would be dimethyl propane. So that should help you for this part. So I'll give everyone another minute or so to look through them. And we'll go through them. And so if you're in the chat too, you can start typing out like what you have or what you think the names are, and we can go through them. All right, let's start going through them. And then so you could approach this, a number of different ways. I'm just going to start with kind of what I would say the obvious one is first. So just the linear chain. So 1, 2, 3, 4, 5, 6, 7. And I always double count my carbons just to make sure. And so what is this one called? And we can double check that it is H16. So it would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that works out. And of course, how many carbons are in this chain? What would be its name? And don't forget, right, we have our prefixes here to help us. So hept, that's for 7. So the straight chain is heptane. Now what could we do? Let's just make it 6 carbons. 1, 2, 3, 4, 5, 6. And then we could put, and this is where you have to do some thinking. So you could add a carbon there, or add it 1, 2, 3, 4, 5, 6. Add it there. Then ask yourself, is this the same structure? And so you should be able to tell that by rotation that it is. So right, this is just one structure. So you have to be careful you don't draw the same structure. So then what would this one be called? So we have 1, 2, 3, 4, 5, 6. And so this is where you want to number them. And so you could number, so 1, 2, 3, 4, 5, 6. If you were looking at this one, I would start on this end because again, you want that methyl to be on the highest priority. You could also look at this chain and notice it would give you the same 1, 2, 3, 4, 5, 6. So either way, right, it should give you the same answer. So you have a 6 chain. Then what carbon is our methyl group in? So notice it's on the 2 position. So this would be 2-methyl hexane now, since we have a 6-carbon chain. Now, could we have added, so let's go back to our hexane structure. Where else could we have added that methyl group? 1, 2, 3, 4, 5, 6. If we added it to this one, is that different? So can we make any other chains? So 1, 2, 3, 4, 5. So that's not the longest. So this is still the longest. 1, 2, 3, 4, 5, 6. If we had added it to this one, that would also be the same by rotation. And so now let's label our carbons. So 1, 2, 3, 4, 5, 6. So now this would be 3-methyl hexane. So what else could we do? So now we're at hexane. So now let's look at pentanes. What can we do? So let's draw out our pentane structure. 1, 2, 3, 4, 5. So where could we put our carbons? So let's just see, could we add an ethyl? So 1, 2, but look at what this does. So now we have 1, 2, 3, 4, 5, 6. So now that would become our longest chain again. 1, 2, 3. So this doesn't work for pentane. So let's see what other combinations we could do. So going back to our pentane, what if we stuck some methyl groups on there? So where could we stick these methyl groups? So we could do it on different carbons. So there might be quite a few combinations. So I could also stick them on this carbon. So have we created any longer chain? So 1, 2, 3, 4, 5. But that would still give the same answer, because you still have 2 methyls coming off that second carbon. We could have put them there. That would have given us the same structure. Where else could we put them? They could both go in the center here. Any other combinations? Oh yeah, I missed. Missed one combination. So we could also put it on the second and the third. Of course, we could put it there and there. That would also be second and third. So that wouldn't change anything. So let's see. Let's start naming them. So this first one, what is this called? And so, you know, prioritize your carbons. And in this case, it wouldn't matter which case you go. You could go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. They would give you the same answer because this is still either on the 2 or the 4 carbon. And so you're just trying to get, again, these substituents on your highest number. In this case, it doesn't matter. So this would be 2, 4 dimethylpentane. It's again 2 methyl groups. So what about this one? So in this case, I put them on this second one here. So I should label this 1, 2, 3, 4, 5. So this means I have 2 here. So this would be 2, 2 to indicate that both of these methyls are on this second carbon. So dimethyl pentane. Now what about this one? So again, this one we could label either 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5. Either way, this is carbon 3. So that's 3, 3 dimethyl pentane. And then this last one, so I started on this one, so I should label this as 1, 2, 3, 4, 5 to give it the highest priority. So this would be 2, 3 dimethylpentane. So what other combinations could we do? So what if we took pentane so we had tried sticking an ethyl here. That didn't work. That didn't work. What if we did the ethyl here? Does this give us, let's check. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So we didn't create any longer chains. And so either way, this is carbon 2. So I'm going to count here. 1, 2, 3, 4, 5. Now we can have an ethyl group in this third position. So remember, we couldn't have 2 ethyl pentane. That didn't work out since we got that 6 carbon chain. But putting it here in the symmetrical position seems okay. So now we can say 3 ethyl pentane. And then let's see. So it gave us a hint. So there's supposed to be 9 of them. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're missing one more. So let's see if we can figure it out. And so let's see what happens. So if we have butane, or start with the butane structure. So 1, 2, 3, oops. 1, 2, 3, 4. So butane. But then I need 3 more carbon. So what could I do? So I could go 1, 2, 3 maybe. 1, 2, 3. So that's the same thing, right? So it doesn't matter. So I could label my carbons 1. Oh, so that doesn't work. So I want the highest priority to have these 2. So 1, 2, 3, 4. So this one would be 1, 2, 3, 4. And so this would give us 2, 2, 3. So again, indicating that we have 2 methyls on the second position, 1 on the third, and then trimethyl, since these are all methyl groups, butane. All right. Excellent job. Any questions about that? So now I want to take a look at cycloalkanes. So cycloalkanes, they now have 1 degree of what's called unsaturation. And so they have a different formula of CnH2n. And so I want to point out the 3D structures of these because it gets interesting. And so I wanted to show it large for a second. So here's our straight chain propane. And, you know, obviously it's missing some hydrogens because what I want to show is we're going to have to kind of strain it to get it into that cyclopropane position. And so let's look at that. So notice it has a little bit of ring strain. And so that is true. So these things are strained, so that causes issues with energetics there. But this is mainly, you know, planar. And then we can have, so cyclobutane, and I'm going to switch to my other molecule kit now. Let me go over here. We can look at them. So there is the square cyclobutane. So again, it's mainly planar, but it has a lot of ring strain in it. So now let's add another carbon to that. So cyclopentane. Oop. Just opened it. So there is cyclopentane. And then cyclohexane is even more interesting. Let's take a look at its 3D structure. So cyclohexane does not lie flat. So it has 2 different conformations. And so I'm trying to get my molecule kit to behave. And so this, hold it like that. So that is its chair conformation. Where it's like this. So one side's up, one side's down. So you can see this. It's kind of hard to see. So kind of the front carbon is up while the back one is more down. Could also be in what's called a boat structure. It looks like that. And see if I can draw this. 1, 2, 3, 4, 5, 6. There we go. There's my boat structure. So chair, boat. So chair is the more favorable conformation. So it's just where they have more space between them. Again, I just want to point out that these are not totally flat. And so cycloalkanes are named similarly. So let's look at some example. So let's look at this one example here. So 1, 2, 3, 4, 5, and then it has a chlorine, a bromine, and a methyl group. And so the question is, well, how do we name it? And so we have to kind of label it by priority. And we go in order too. So we can't just go, right, 1, 2, 3 or anything crazy. And so to give everything the highest priority, this will have to be 1. This will be 2. This will be 3. But then when we name it, so because the same rules apply. So if we go back, where our naming rules? Oh, wrong page. So it says assemble the name listing groups in alphabetical order. So now, and this is where it might get kind of confusing. So we've labeled this, we have our priorities. Now when we go to name it, we have to start with bromo, since this is in front. And so, of course, let's identify. So this is our longest chain, or rather, our longest circle here is pentane, or cyclopentane. So, and now let's add everything in front. So again, bromos first because it's alphabetical. So 2 bromo. Let me get that webcam out of the way. 2 bromo. Now it's chlorine. So 1 chloro for our chloro group. And then 3 for our methyl. So 3 methyl. And now we can add cyclopentane. So let's look at another one. So what would be this name? So this one, assign our priorities. So this carbon has 2 things on it. And so this gets carbon 1 here. So 1, 2, 3, 4, 5, 6. So cyclohexane. Now there's 2 methyls. So 1, 1. Oops. And I already screwed up. So my mistake was I didn't start with bromo. So 2 bromo. I just got excited by the methyl. So 2 bromo, 1, 1 dimethyl cyclohexane. So any questions on those? All right, so let's look at kind of the end of the chapter, which is, what is all this used for? And so primarily hydrocarbons are fossil fuels. Honestly, I'm a huge fan of fossil fuels. I think we'd kind of mentioned it last week. We talked about radioactivity and energy density. And, I'm huge for nuclear energy. I do believe it's the way of the future. But we can't forget that all these different energy sources have also high energy density. I'm all about that energy. And so natural gas is mainly methane. So again, that's that CH4. And so methane is odorless. And so they add mercaptan to methane. That's what gives it that kind of rotten egg smell. And so I just pulled up, again, some energy density to point out. So natural gas has a really high energy density, 55 megajoules per kilogram. So that's good. It's a little bit higher than crude oil, diesel, and gasoline. So that's kind of interesting. So again, natural gas, pretty decent. And of course, unfortunately we get this methane out through mining and fracking, which we could argue about the environmental impacts of it. But as with everything, moderation is always key. Can't be dependent on any one energy source either. And then so petroleum, of course, is also really important. And so what I have kind of drawn out here is a little schematic of how they actually refine all the petroleum. So if you take your crude oil, this is basically a huge distillation column. So a simple distillation, so this is just simple distillation. Let me draw this out better. I don't know what this was supposed to be. So we have our heat source and our flask with whatever liquid we want to purify. And then that heat source takes it up. So it evaporates and it cools back down and condenses here as liquid. So this is a simple distillation. And so they take the same concept, right, of boiling things and separating them by their boiling points. But it's instead a huge fractionating column. So at each of these levels, there's like a large amount of material to kind of help fractionate and keep the temperature consistent. Like you could imagine a bunch of beads, essentially, to keep the temperature consistent in each layer. And so what you find is, of course, your volatiles, right? They're going to have the lowest boiling point, and so they're going to go the highest up, right? And so they're going to go up here to the top of this column, and then they can be separated out in the high boiling range. So that can be, butane and lighter products, potentially even getting out methane in this process. And then you have all the way down here these heavier, higher boiling stuff. So of course, if they're higher boiling, it's going to take them a lot of energy. So they're not going to make it up this column, and instead they can be refined out. So residual fuel oil, heavy gas, diesel, and then it goes up kerosene, naphtha. There's a gasoline blending. So gasoline tends to be octane. I think we mentioned that. And then just looking at boiling points of alkanes. So let's think back. I think we talked about boiling points roughly in last quarter. So what type of intermolecular forces do alkanes have? Are they polar? Are they non-polar? I'm just showing, right? We're just dealing with carbons and hydrogens. And so the thing is that these alkanes are always non-polar. And so if they're non-polar, they only have those weak intermolecular forces. So they have van der Waals or London dispersion. And so that means they're going to have relatively low boiling points. And so you can see that in this graph here. And of course, if you add, more alkanes, the boiling point increases. Isoalkanes, so any branching that tends to lower the boiling point since you have less overlap. So for example, your alkanes, right, they can kind of pack in like that. And so that increase surface area. And so that surface area for the intermolecular, so between molecule forces. So increased surface area, so those van der Waals forces, right, have more surface area to interact versus anytime, let's just take that neopentane example, So much less. And so now comparing these two, so neopentane versus like pentane, neopentane would have a higher boiling point because it has less surface area for those intermolecular forces. And Tang is my cat's bombing our session here. So let's look at combustion. So I mainly wanted to look at what's called, and your book makes the distinction. So this would be complete combustion. And so let's just look at, well, what is a combustion reaction? So the simplest form is it can be any organic molecule taking the form of, right, any carbon plus hydrogen and sometimes oxygen in there. And then you burn it in oxygen. And then the products are always CO2 and water. And of course, you would have to balance this out. So let's just look at kind of the simplest example of combustion here. So let's look at methane. So methane plus oxygen gives me CO2 and water. So let's balance that out. So I have four hydrogens on the left side. So I need to put a 2 there. Tang, I need you to get out of the way. I can't see. Okay, let me fix my typos. So now I'm just balancing the equation. A cat just wants attention. And then let's see. So now 4 oxygens on this side. So it looks like we need a 2 here. And now everything looks balanced. And so let's look at a couple of things. And so we often say that when things undergo combustion, they get oxidized. And the simplest definition of oxidation is just the addition of oxygen. But we could also quantify it by looking at its oxidation states. And so let's do both. So we can kind of see that carbon is getting oxidized, but let's look at it formally. And so before we go on, and I believe we covered it, but let's just go over it really quick, just in case, so everyone's on the same page. So we have this acronym oil rig. And so we said oxidation is losing electrons, and reduction is gaining electrons. And so let's look at this formally with its bookkeeping. So hydrogen we always know is in the 1+ oxidation state. That means carbon is -4 to balance that out. Anything in its elemental form has an oxidation state of 0. Now oxygen and compounds have a -2 charge or a -2 oxidation state. So now carbon is +4. And so carbon went from -4 to +4. So it became more positive. So that means that it underwent oxidation since it's losing electrons. And you can see that, of course, if one element is getting oxidized, there has to be somebody that is getting reduced. So in this case, that's going to be oxygen. So oxygen became more negative and went from 0 to -2. So it gained electrons. Welcome in the chat. Let me know if you have questions. So let's just write. So carbon is oxidized, then oxygen reduced. And so you may have heard the term incomplete combustion. And this is where you don't have enough oxygen to do a complete combustion, and instead this leads to the formation of CO, carbon monoxide. So this is bad. So this could be, potentially very hazardous too. Like this is, some of the dangers with fireplaces and anything like that, anytime you're burning. And so it's always good just to have a CO2 monitor, a CO monitor, a CO monitor, especially if you use different alternative heaters. They could be giving off a little bit of CO, so it's better to check. Since, of course, CO is odorless, colorless, and you wouldn't know that you were, breathing in CO until it was too late and you were sleepy and then potentially pass out and not wake up. All right. I think that is a chapter. How are we feeling? Are there other questions right now? So now I'm just glancing at your homework. So some naming stuff. I feel good about that. I feel good that we can name. So it's a lot of the same stuff. Oh, let's look at one thing that we didn't quite cover, but I noticed it did pop up on your homework. So it's asking for you to draw this structure. Let's just start a new page of cis 1,2 dimethyl cyclopentane versus trans 1,2 dimethyl cyclopentane. And so take a minute or two, see if you can think what the difference would be. I won't draw out. Well, I will, but I'm going to make our structure first. Show us the difference. And this is why the molecule kits are really important. Because we could also just draw it, but maybe not really appreciate it. And so let's go to our webcam scene here. And so just so we're all kind of oriented properly, you can tell I have my cyclopentane drawn out. And then I added my 2 methyls to it, so in my 1 and 2 position. And so is this cis or trans first of all? And remember, cis is the same side. So this is cis, right? They're both going kind of up. And let me draw it. And I would probably draw them kind of up like that. So you can tell that, yes, they are both going up. You could both draw them down too, right? That would be the same thing. They can be up, they could be down. Right. Up, down, same thing. And so trans would be, so I'm going to take one of these and then just move it to the other side. And so you can see the difference now, right? That takes up a different amount of space. So there's our ring. Again, there's distortion in that ring. Not completely planar. So you can tell actually this carbon's a little puckered up on our cyclopentane. And so now there's our structure. And so I would draw for the trans one. So this is cis. And then trans. So again, trans are opposite sides. So I would draw one kind of going up like that. And then the other going down. So they have opposite stereochemistry there. Then the rest, I think, should be relatively easy, or at least we have covered it. I'm just taking a glance at your homework. So again, more IUPAC naming, so that should be relatively straightforward. And then, so our alkanes water soluble, so that goes back to what we're saying about this. So again, they're going to be non-polar, so they're not miscible with water. Yeah, so the rest of the homework looks pretty straightforward, just going through it. I think it'll be good practice to do it. And so let me know if you have other questions. I'm going to stop the stream now. I'll hang around, of course, if there are questions. Thanks for the views in the chat. And if you want to set up some office hours appointments with me, just send me an email and we can do that as well. So thank y'all. Have a great rest of your day, and I'll see some of you in lab today.